All right, so let's take a break from stoichiometry and calculations and talk about some theory and concepts. I mentioned earlier the kinetic molecular theory of gases. Here we're going to explore the four postulates of this KMT, kinetic molecular theory. Postulate number one of this theory that defines ideal gases says that ideal gases consist of point particles. These particles have negligible volume, so they take up a minuscule amount of space, but that they move in constant, rapid, random motion. So gas particles are in constant motion, but they're just little tiny point particles that really don't amount to much. Secondly, these particles are so small with respect to the volume that they occupy that gas is mostly just empty space, sort of like an atom is mostly empty space. Anytime that these tiny little point particles do hit each other, though, or collide, those collisions are elastic, meaning they don't transfer energy to other particles or to walls of their container, so that these particles remain in motion and aren't bogged down by things like attractive or repulsive forces between particles. Lastly, the average speed with which these particles move determines their absolute temperature. Temperature is directly related to the average kinetic energy of a group of gas particles. The four empirical gas laws, Boyle's, Charles', Avogadro's, and Amundsen's, can all be explained under this kinetic molecular theory. In order to explain all four of those gas laws that were based on experimental evidence in the vein of this theory, we'll think about a closed container like an aerosol can with a gas inside of it. We can imagine pressure, which is force applied over some surface area, like, say, the walls of a canister. Pressure is a result of gas particles moving in constant motion and therefore, just by sheer statistical coincidence, eventually hitting the walls of their container and applying a force to those walls. If we decrease the volume of that container, if we make a smaller and smaller canister, if volume decreases, then the likelihood of bombardment with the walls of the container for any given gas particle goes up, and therefore pressure goes up. This explains Boyle's law. As volume decreases, pressure increases, and vice versa. Secondly, if we imagine our container at a set constant volume, increasing the number of moles of gas, or just increasing the number of particles of gas inside, would mean that there are now more particles and therefore a higher likelihood of particles bombarding the walls of the container. Pressure would go up. Or, alternatively, in order to keep pressure the same, we'd need to make the volume bigger to be able to equivalently house, at an equal pressure, a larger number of gas particles, so that as number of moles goes up, volume goes up. Avogadro's law. Lastly, if we increase the temperature for a set number of particles inside this canister, because temperature is related to the average kinetic energy of particles, the force with which particles hit the walls increases. And pressure goes up. Amundsen's law. Or, to maintain a constant pressure, we need a bigger volume container. Charles' law. This last idea is the most applicable to us for thinking about chemistry. So, as temperature goes up, according to the kinetic molecular theory of gas, the average kinetic energy of particles increases. And although kinetic energy is the real central focal point of this idea, we can tie kinetic energy to a speed or average velocity instead. If you've taken a physics class, you might know that kinetic energy is equal to 1/2 mv squared. That's 1/2 times mass times velocity squared for a moving object. So we can say that if kinetic energy is increasing for a particle with a constant mass because it's not reacting, the velocity of that particle must be going up. So as temperature increases, the mean speed of a gas particle must be increasing. Or if we have a distribution of particles with different masses, we can also say that at a constant temperature, because all of these particles have the same average kinetic energy, regardless of their mass, at a constant temperature, in order to compensate or overcome for mass differences, particles that are heavy must move slow, and particles that are lightweight must move fast. This also maybe makes some intuitive sense. The heavier something is, the slower it moves at a constant temperature. The lighter something is, the faster it's able to move. This means of comparison from the kinetic molecular theory of gases allows us to predict how fast a particular gas particle is likely to move relative to others at a constant temperature, given its overall molar mass. For example, if we compare the average speeds of oxygen, nitrogen, water vapor, helium, and hydrogen gases like you see in this plot here, we see that the average molecular speed, which is the peak of any one of these distributions, is farther and farther out along the x-axis, the lighter some gas particle is. Hydrogen, which is the lightest of these molecules or atoms of gas with a molar mass of 2, has a peak in its distribution of speeds way out here at a really high velocity. Oxygen, O2, with the greatest molar mass of 32, has a peak in its velocity distributions that's at the lowest point along this x-axis. So we can generalize this and say, similarly to the previous slide, that the greater the molar mass of a gas particle, the slower it will travel on average at a given temperature. This relationship allows us to do something like rank the relative speeds of gases. Here in this example, we're going to compare hydrogen, carbon dioxide, argon, sulfur hexafluoride, uranium hexafluoride, and krypton gases, all of which are at the same constant temperature, through comparison by relative speeds. To do this, let's come up with a list of all of the corresponding molar masses for these gases. I'm going to have a table that lists the gas, the molar mass of that gas, and then eventually a rank for speed. So you might want to take a few moments and fill this table out for yourself, then come back and see the results. All right, let's fill in molar masses. I'm just going to do to the ones place. So I'll say hydrogen has a molar mass of 2 for all intents and purposes. Carbon dioxide, a molar mass of 44. Argon's molar mass is 40. SF6, 146. UF6, 352. And krypton, 84. In terms of rank, we expect that the heavier a particle, the larger the molar mass, the slower that gas particle moves. So we should expect that the heaviest particles are the slowest. UF6 is the heaviest, largest molar mass of this group. This is going to be the slowest, or if all of these gases were in a race, this would finish 6th So which finishes first? Which is the fastest? Well, it stands to reason that the lightest particle must be the fastest. Since hydrogen is the lightest of the gases on this list, we'd expect it to come in first in a race. All of the rest of the gases will follow in order of molar mass. The second lightest is argon, next carbon dioxide, then krypton, second to last, second heaviest, is SF6. And thus we can rank comparatively the speeds of these 6 gases. That concludes Chapter 9 and our discussion of gases, which overall really isn't too bad. Our main concern is identifying appropriate gas laws to use. After we've discussed gas laws, we talked about comparing gases on the basis of speed using the kinetic molecular theory of gas. Next, we'll cover other phases of matter, liquids, solids, and solutions.